In this video, we're going to be factoring polynomial expressions completely. Let's take a look at our first example. Here, we have x to the third minus 27. Now, as we look at this, we don't see perfect squares. However, here we have a perfect cube root, and 27 is also a perfect cube root. And because our symbol between the two is a subtraction, then we're going to factor the difference of cubes here. So we're going to go ahead and take that cubed root of our first piece, which is going to give us an x, and then we're going to take the cubed root of our second piece, and that's going to give us a 3. And now we can go ahead and write that as our factor. There's a formula for factoring the difference of two cubes, which is if you have a u cubed minus a v cubed, that can be factored as u minus v times u squared plus uv plus v squared. And so we're going to go ahead and use that. And so here our u value is going to be our x, or our first term, and our v value is going to be that 3. So we're going to put an x into all of the u places, and we're going to put the 3 into all of the v's places. All right, so let's go ahead and let's fill that in. So we're going to put in our x here, 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 and we're going to put in our 3 here, here, and here. And now we just need to simplify that, which is going to give us x minus 3 times x squared plus 3x plus 9. And that is now simplified completely. And we're done with this problem. Let's take a look at our next problem. Here we have 3x to the third plus 192. So we're going to go ahead, because 3 isn't a perfect cube, and we're going to try and see if we can take out a common factor of 3 here and look and see what that gives us. So by doing that, we see that we end up with a 3 times x cubed plus 64. And from here, we can see that our first piece is a perfect cube, and that our 64 is a perfect cube, and there is a plus sign between them. And so here, we can factor using the sum of two cubes. That equation is very similar to what we did on the last problem. Here we see that the changes are, by having a plus sign between our u cubed and our v cubed, changes our initial symbols to be u plus v, and then u squared minus u times v plus v squared. So again, our u, go into all of our u spots, we'll be able to put our v into all of those v spots. So our u will be the cubed root of x cubed, which is x, and our v will be the cubed root of 64, which is 4. So we'll go ahead and we'll fill those in. And we're going to go ahead and simplify that then, which gives us x plus 4 times x squared minus 4x plus 16. And we now have this completely factored. So if we look at our next example, we have x squared minus 7x plus 12. So here we don't have a leading coefficient, or rather the leading coefficient is 1. So we're going to see what we can do to break down this 12. So we want to know what numbers will multiply to 12 but add to 7. We could try 1 and 12, but we know that won't add to 7. Or even 2 and 6, but that won't add to 7. But if we try 3 and 4, we can get those to add to 7. Now right now they add to a positive 7, but we need them to add to a negative 7. So in order for that to happen, we're going to need to have the 3 and the 4 both be negative. So that way they'll add to a negative 7 and still multiply to that positive 12. we're now ready to write our factors. So here we'll have x minus 3 and then x minus 4, and we can see that they've been completely factored. And so we're done with this problem. Let's look at our next example. In this problem, we have 2x squared plus x minus 15. Here, we have a leading coefficient that is not 1, so it won't be just as simple as the multiply-add trick. And rather than writing out all of the different possible factorizations, I'm going to use a method called the box. I call it the disco box because it's kind of fun. So I'm going to make a box with 4 squares in it. Then I'm going to take the first thing and put it in the first box. Then I'm going to take this last thing and put it in the last box. So how do you fill in the 2 other boxes? Well, what we're going to do is we're going to go ahead and take this 2x squared and our negative 15. So again, that was the first thing and the last thing, and we're going to multiply those together. And that's going to give us a negative 30x squared. Now we're going to split those x's and put 1 x in each of these boxes. Then we want to know what 2 numbers will multiply to a negative 30 but will add to the positive 1 up here. Well, we know that 2 and 15 probably won't work, but 6 and 5 will work. But if I want it to be a negative 30 and I need it to be a positive 1, one of my numbers needs to be negative. And because I want the 1 up here to be positive, I'm going to choose to keep the 6 positive and make the 5 negative. And now we'll take these 2 numbers and put them into our 2 remaining boxes. And it doesn't matter which box you put it into, because you'll end up with the same answer in the very end anyways. So I'm going to put my 6 here and my negative 5 there. And now we're going to go through and simply see what do each of the columns and rows have in common. So let's start here. What do these 2 boxes have in common? They have a 2 and an x in common. So we're going to go ahead and we're going to write down 2x right there. What do these 2 boxes have in common? Well, they both have a 5 in common, and they both have a negative, but really this front negative is what drives writing down a negative. If the first box is negative in the 2 boxes that you're looking at, then you're going to write down a negative sign for the number that you're pulling out. So here we'll write down negative 5. And now we're going to look at it vertically. So here I want to know, what do these 2 boxes have in common? And these 2 boxes only have an x in common. So I'm going to write down an x. And now we want to know, what do these 2 boxes have in common? And those both have a 6 in common. And it doesn't matter that the bottom number was a negative, because the 6 wasn't negative, we don't need to take a negative out. So we're going to write down a 3 right there. The next thing we're going to do is our final piece. So we're going to go ahead and write down our factors, and it doesn't matter where you put them. So I could put my pink numbers first, or I could put my pink numbers second. That's not going to matter. So let's go ahead and let's put our pink numbers first. 2x minus 5, and then we're going to put our orange number second. It was an x and a positive 3. And we can't break those down anymore, which we shouldn't be able to do if we did it right. And to make sure that up in the beginning, if there was any common factors, we'd factor those out, but there weren't any, so we didn't need to. So we have factored this completely, and this, let's just move that back, there we go. And this is going to be our solution right here. Let's take a look at our next example. Here we have 12x squared plus 7x plus 1. So here we have another one where we have a leading coefficient that is not a 1. And we look at it, there's no common factors to factor out, and so we can use our box method here as well. So we're going to go ahead, draw our box. Remember, we're going to take that first thing, it's going to go in the first box. We're going to take the last thing, and it's going to go in the last box. Then we're going to multiply those together and take our x's and split them to the leftover boxes. And then we want to know which two numbers will multiply to 12, but we'll add to that positive 7 that we need. So we're going to use 3 and 4. And so those numbers are going to go into our leftover boxes. And again, it doesn't matter which order you put them in. So I'm going to put my 3 here, I'm going to put my 4 there. And now we're looking for numbers that they have in common. So here we see that the commonality, the common number, is a 4x. Here we see that there isn't a common number, so we're just going to write down a 1. Looking at these boxes, we see that they both have an x in common and that a 3 goes into both numbers. And here we see that those also don't have any numbers in common, and so we're just going to write down a 1. And we're now ready to write down our factors. So remember, it doesn't matter the order you put them in. So we're going to write down 3x plus 1 first to show you that it doesn't matter. And then a 4x plus 1. And we should be completely factored now. And we're going to go ahead and we can check and make sure this will not reduce anymore. And 4x plus 1 will not reduce anymore, which tells us that we are completely factored. And so we are done with this problem. And for our last problem, we have x to the third minus 2x squared minus 3x plus 6. Because we have 4 terms, we can factor by grouping. So we're going to go ahead and we're going to group here and here. So now we're going to look at our purple group and go, what do those both have in common? And those both have in common at least an x squared that can be pulled out. So we can rewrite that as x squared times x minus 2. Then we look at our pink group and we see that we can factor out a -3 from both. The reason we're choosing a -3 instead of just a regular 3 is because of this negative symbol right there. If that leading term is a negative, you need to take out a negative as well. So we're going to go ahead and take out a -3 from our pink group. And that's going to leave us with an x and a -2 there. And now we're going to put things back together. So we're going to find our green things and they're going to go together. So we're going to write down x squared minus 3. Then we only need to write down one of our blues, so x minus 2. Because we're saying there's a group, like we're pulling those out. So what that's kind of like, let me just go back a second and kind of explain that a little bit better, is that if we look at our terms, we have a term here and a bigger term and another term there. So what do both of those terms have in common? Well, both of those terms have an x minus 2 that can be pulled out. So we're going to go ahead and we write that on the front, x minus 2, and then we have what's left over, which is our x squared minus 3. And at this point, we're going to double check, and we can't reduce our x minus 2 anymore. And we can't reduce our x squared minus 3 because 3 is not a perfect square, which means that we have fully factored or completely factored this problem. And we're done.